So I don't need an introduction. You've heard me a couple of days ago. The purpose of this lecture is to start somewhere before I left off 2 days ago. And if you remember, I told you about quantum simulatability. And so I'm going to start here at what I consider a key result in the field. This was the Aharonov and Tashma sparse Hamiltonian lemma that tells us so the question of whether a system is efficiently simulatable, if the Hamiltonian satisfies this set of conditions, then it is efficiently simulatable. So I covered it last time. I mentioned to you that the cost of the simulation by Aharonov and Tashma is all polynomial. So it's polynomial with respect to the number of bits that specify the problem size, the sparseness parameter of the Hamiltonian, that itself is a polynomial function of the number of bits, and its inverse, it's polynomial in 1 over epsilon, where epsilon is the allowed trace distance. So the allowed distance between the state you should get and the state you get from your quantum computer. And then the game is how to bring down these costs. So once the efficiency was established in Aharonov and Tashma's work, then the issue is how to get down the costs to the limit, and that's what brings quantum simulatability down into a regime where it's experimentally viable. And so early on, and I mentioned actually there were some discussions about adiabatic quantum computing today, which has a number of issues. The Aharonov and Tashma work, I remind you, was motivated by having a computer science attempt to understand the issues concerning adiabatic quantum computing. And in that work, published in Stock in 2003, there was, that's the cost. So the simulatability algorithm that was developed by Aharonov and Tashma has a time cost, i.e. the number of gates, that scales polynomially, but a very high power of the number of bits, and the space cost is of the order of n. So it means the space cost of the quantum computer is linear in the number of bits of the problem size. Then Andrew Childs, in the same year, in his thesis, brought the cost down from, he brought down the cost here from n to the 9 down to n to the squared roughly, kept the time cost the same, and then there was some work a few years later I did with Richard Cleve, Dominic Berry, who was a postdoc of mine, Graham Mahokas, who was a student at the University of Calgary, and we figured out what the limits were and brought the cost down. In particular, I discussed log star n last time. It's effectively constant, so we brought the cost down from t to the 3/2 to nearly linear in time and raised the space cost, but the space cost going from n to log star n is basically the same as n. Log star n is so small. And then the way the algorithm works is that we have a unitary evolution u that's generated by some Hamiltonian. Each hj generates gates. So remember I talked about color. J was the color index, and it's related to what Ray talked about this morning, for example, a set of pulses. So if you imagine every kind of pulse you want to generate is done by some colored button. So you just hit a set of colored buttons. Then the idea is M tells you how many different types of pulses, how many different colored buttons you need, and uj is the particular pulse generated. And in this case, in this algorithm, the Hamiltonian is decomposed into a sum of Hamiltonians that are one sparse. That means when they're written as a matrix, no matter how big they are, there's no more than one non-zero element in every row or column. Okay, and then the idea is that we take the unitary evolution and it's just generated as a sequence of those gates. So I've put in a picture to help you understand what's going on. In a broad view, this is the way the simulation algorithm runs. That what happens is we use a formula, that's the Trotter formula or the Trotter-Suzuki formula. We make our unitary evolution, so the u tilde, remember tilde was the approximation on the quantum computer, so we take our u tilde, it's a product of unitary evolutions up to some capital N. That's the number of pulses we need to be able to operate. There's some approximation, and then what happens is these indices, J1 to Jn, just says which color. Like it says, hit the red pulse, like the red button, blue button, green, red, blue, whatever. They can repeat, and each one of the buttons executes the following step. So here, the idea is this is the letter L, not the number 1. And so the idea is that we have a basis set. The basis set is the computational basis set, strings of zeros and ones in our qubit register. And then everything else going in is 0. Remember I mentioned last time that in order to have efficiency, every qubit has to be recycled. So we feed this in, and the output of whatever's going on here is the first evolutionary step acting on that. So your basis element goes from L to uj1 tilde of L, uj2 tilde of L. And so this broad view circuit diagram represents the idea that we want to be able to execute the Trotter type expansion. See? So remember we talked about Trotter-Suzuki last time. The idea is to use the Trotter-Suzuki expansion to then create the quantum circuit that's going to execute it. And then if the Hamiltonian is diagonal, so if we have a strictly diagonal Hamiltonian, so a diagonal Hamiltonian is trivially 1 sparse, then the way to execute that, and this is the only picture I know in published literature, is only in Andrew Child's MIT PhD thesis, and this is the way it's done. We just have a controlled D operation, where D is the value of a particular diagonal element. This A can be put in some superposition state, and then this execution will effect the evolution due to a diagonal Hamiltonian. And then I mentioned to you that if it's off diagonal, there's another circuit, which I didn't go into. Essentially, the A, you have an A and a B, and then there's a transposition element. So it's kind of a permutation. Turns out that these W's are saying that if you take a 1 sparse Hamiltonian that's not diagonal, you effectively permute it to a diagonal, then do child circuit, and then permute back. So once you know how to create a circuit that will effect the evolution due to a 1 sparse Hamiltonian, then you just have to do a basic pairwise bit permutation to be able to do what you need. And so Aharonov and Tashma then developed that circuit, which can be based on this particular type element. So going on inside of here, I can now fill in. And the filling in is simply that we have those qubits here. This is the basis element for the state that's going to be evolved. And then it turns out that we need the qubits to write on the qubits the row and column of the Hamiltonian. It's a query model. So the row and column elements for the Hamiltonian, it's 1 sparse. So all we do is given a basis element L, it's got, so L could be thought of as the row index of the Hamiltonian, L prime is the column index. So we just store the maximum of the row column index, the minimum of the row column index. These are only stored to be able to recycle the qubits later. And then if it turns out that we're working with the right 1 sparse Hamiltonian, that's the right color button we hit, then we write the approximation of the Hamiltonian matrix element. Otherwise, we just leave it as zeros and execute the step. So the step here, once that's done, is the unitary evolution using either child circuit or child circuit augmented by permutations. And then this is the cleanup phase, and the cleanup phase restores all the qubits back to 0, so we don't have a hidden exponential overhead. And just to show you, I even put down here the actual circuit. This is the maximum of the L and L prime, the minimum of the L and L prime, qubit string, the Hamiltonian matrix element, and Scylla. And you can see it's just a bunch of controlled operations that will effect that evolution. So I've got it down to the point where we can take this simulation and we can even tell you, like if given some simulation to be done, we're able to map it exactly to a sequence of pulses. As Ray talked about with his NMR, we can turn it exactly into the sequence right down to the experimental side. Okay. Then the idea was, how do we get the number of buttons we have to hit down to a minimum? So I covered last time, in order to get it down, we make use of the Lee-Trotter-Suzuki formula. Lee-Trotter-Suzuki, so Suzuki developed his work with ordered operator exponentials with respect to some real valued x, but the results are valid by complex continuation, so x can be a complex number. And then the idea is that Suzuki gave some order expansion. And then the idea here is that this is the order expansion. You have some sort of symmetrized formula on that sequence of operations. So in this case, you just have two color buttons, H1 and H2. You hit H1 for time t on 2r, H2 for time t on r, H1 for time t on 2r, and that will approximate the evolution generated by H1 plus H2. And then and I'm only going quickly because I'm just repeating what was done a couple of days ago to refresh you for what's coming. And then the idea is that if you want to go to higher order, you simply say, well, can't we have like an H1, H2, H1, H2, H1 term, or higher order? And that's the idea of the Suzuki expansion. And I'll just mention that in here, in here you can see there's a square and 1. So it turns out that every iteration of the expansion involves 5 terms. So you'll see the number 5 come up again and again. And when the number 5 comes up again and again as a base of exponents, it's a reflection of the nature of the Suzuki expansion. You could conceive of different expansions that would involve a number other than 5. So 5, when you see it, is not special. It's just a reflection of this particular algorithm. And then Suzuki proved here that his kth order iteration will approximate up to some order function lambda to the 2k plus 1. Since lambda can be analytically extended, it's true also for lambda becomes it, time. So we can use that to approximate. What I pointed out a couple of days ago is having an order on the right side is not sufficient to be able to demonstrate that the simulation is in fact efficient with respect to all resources. So we did work where we take that part here that says it's of the order of a function of lambda to the 2k plus 1 and make a strict bound. And the strict bound looks very complicated, but the key points, this is a lemma in our work, key point is the true evolution, and the approximate evolution to some kth order is given by some function here, but the key point, tau, is the scale time. So remember that in theoretical physics, everything should be dimensionless. The scale time here is scaled with respect to the highest norm of any one sparse Hamiltonian. So you take every one sparse Hamiltonian, find the norms of each one, take the biggest one, that becomes the fastest rate term, and then the fastest rate term is used to turn time into a dimensionless quantity. And, I keep trying to correct it and I keep forgetting. It should be 1 plus 1 on 2k. And so the idea is that for k large, the scaling is now almost linear. So whereas Seth Lloyd's work had t squared, Aronoff and Tashma and Childs had theta to the 3/2, this brings us down to slightly superlinear in time. So we have a simulation where the number of pulses we need, or colored buttons to hit, is almost as close as you like to linear in time. And I won't go through the sketch of the proof, but I could take questions later. Okay. And then, given that, we then have our theorem, and our theorem says that the number of pulses is no worse than the scaled time with respect to 1 plus 1 on 2k, which can be small. However, there's a subtlety here. Remember I warned you about the number 5? So the number 5 appears here. So it looks like the number of pulses you require is going to grow exponentially with the order of the iteration. So if you naively take the Suzuki expansion and say, we will use that expansion, take Trotter formulas to higher and higher order, in fact, you get an exponential growth here. But by replacing Suzuki's order estimate by a strict inequality, that means we can now optimize. So we can now optimize the order of the Suzuki expansion, and that's done by writing k. The order roughly goes as this. So it's 1/2 the square root of the log base 5 of m, which is the number of colored buttons, tau, the scale time, divided by the allowed error epsilon. Something I emphasized last time, I want to emphasize again. For me, any legitimate approach to simulation must have epsilon as an input. If you don't have epsilon as an input, it's hard. Not only can you not count the resources, but you can't even, you can't figure, it's insufficient information. You can't just do a simulation and verify that it's efficient without that error being an input. And then it means that the number of, under the optimization, the number of pulses that you need is linear here, but there's a small dependence on time t over here, you see? So it's So we brought the cost down from t to the 3/2 to something that looks like t times an exponential involving the square root of t. And then you can, it turns out that you can, under reasonable assumptions, guess an approximation, and it goes something like this. Okay, so now we've brought the cost down. Now I just want to take a bit of time, and I'm going to explain this to you. And here's the question, and I mentioned a couple of days ago, the question that comes up even after I go through this, people will say, why can't you beat the linear limit? And this in our work, this was the hardest part for us, even though it turns out to be fairly trivial. And so the idea is we bring the cost down from t to the 3/2 to almost t, and you say, well, can there not exist a quantum algorithm that will efficiently simulate at a cost that's lower than t? Now remember, when I talk about an algorithm, I'm referring to an algorithm that is written in advance of knowing the Hamiltonian. All you know is that the Hamiltonian satisfies the conditions of the Aharonov and Tashma sparse Hamiltonian lemma. Once you know that it does that, that's it. Your algorithm has to work for every Hamiltonian satisfying that. So if we can find a Hamiltonian that cannot be simulated sublinear in time, then that's enough to prove that there cannot exist a general algorithm, you see? So the idea here is to find a counterexample. If you say to me, surely there exists a Hamiltonian that could be simulated sublinear in t, that can be the case. But all I have to say to you is, I found an example of a Hamiltonian that can't be. And that turned out to be fairly hard to do at first, but now it turns out to be very simple. So here's a formal statement of a theorem, but the idea is the following. Consider a sequence of bits, and the sequence of bits could be generated randomly. It doesn't matter. And then the goal is to estimate the parity of that, right? So, if you add up those numbers, modulo 2, will the answer be 0 or 1? And it turns out that there's a proof based on using quantum walks that shows that you cannot estimate the parity of a string of bits of length n with fewer than n on 2 queries. And that's the lower bound proof that we use to prove that the simulation cannot go sublinear in time. So the idea is, let's say we consider a string of bits, and now consider a simple Hamiltonian that we love in quantum optics, which is the spin Hamiltonian, but it's spin of arbitrary spin order. It could be half, spin 3, spin 5 halves, whatever you want. And so this is like a Bloch sphere for a higher order spin, and I've labeled the states. And all we've done is we say, let's consider the Hamiltonian for spin, and then let's augment it by a single qubit. And the purpose of the extra qubit is it just takes it from the red sphere to the blue sphere if the bit value changes. So when you go from here to here, it does a bitwise addition. If the sum is 1, you cross to the other Bloch sphere. If the sum is 0, you don't cross. See? So it's just a bitwise addition. And the bitwise addition turns out to be important in the proof. Okay? But let me give you some words that will explain what's going on. By the way, that proof of the lower bound on querying, the quantum walk-based lower bound proof on how many queries it takes to learn the parity of a string of bits was done by, it's in the Journal of ACM, American Computational Machines, I think. So JACM, by Beals, Borman, Cleve, Mosca, and DeWolf. Came out in 2001. It's one of the early quantum walk results. And that's where they proved that the parity of a string of n bits requires, with an error of a quarter, requires n on 2 queries. And then we take the Hamiltonian, which is the spin Hamiltonian Jx, and Jx, this is an undergraduate problem, physics problem. The matrix elements of Jx are given by this, and we can calculate the norm of the Hamiltonian, and the norm is capital N over 2, and n is the number of spins we have. So we go from 0 to n. So there are n plus 1 spin states. Remember that our norm is our time scale.
Norm is the largest eigenvalue?
In this case, yes. It's the largest eigenvalue. So in this case, we use the norm of the Hamiltonian in order to be able to determine the rate. So that's our rate term that we're going to use to scale to dimensionless time. And then if we take our Hamiltonian and we start off with the spin at the bottom, then it turns out that in time pi, the Hamiltonian will evolve it to the top. So in that picture, we're saying, how long does it take to go from the bottom of the block sphere to the top? Then we introduce the random bit string xj. That's the one that we don't know the parity of. It's randomly generated. And then we add the ancillary qubit. Remember, that was the partitioning to two block spheres. So L or L prime, J is the spin index. L and L prime can only be 0 or 1. It's which of the two block spheres. And then what happens is it only crosses between block spheres. So the string of L and L primes are done such that the sum of the L and L prime add modulo 2 or XOR to the value of the string xj. So that sequence is constructed. And then what happens is we make sure that the Hamiltonian only crosses from one sphere to the other if the sequence of two the sequence of the two L's is going to be different. So we now have our evolution, and this just reminds you, the evolution from 0 to n went as took time pi, and so the evolution, even adding that ancillary qubit, doesn't change. So the fact that we've taken the block sphere and made a copy doesn't change the time of evolution. Okay, so then what we do is we allow it to evolve. That's over time pi. And then if we measure we just measure which block sphere it's on. That's measuring the ancillary qubit, 1 qubit. If we measure the qubit, we learned the parity of the string of bits. You get the idea? So if we construct that perfectly reasonable Hamiltonian evolution, and we say which block sphere did the system wind up on, we've learnt the parity of the string of bits. But we have a lower bound. It takes at least n on 2 queries even to reach an error of epsilon equals a quarter. Now, in order to do the evolution, we have to do 2 queries to the string for each time we query the Hamiltonian. So we query the Hamiltonian to simulate its evolution. Okay, like you say, what is the value of the non-zero column element in row 3? That kind of thing. And it takes two queries to the bit string in order to be able to answer that, because we want to know if the string had a change in value or not. Remember, if it changes value, then the particle goes from one block sphere to the other. If it doesn't, then it doesn't. And so it means that if we perform n on 4 queries to the Hamiltonian, there have to be twice as many to the xj. And then it tells us that it tells us that if we only perform n on 2 queries to the xj, that lower bound proof tells us the error has to be at least a quarter. So this is our scaled simulation time, the norm of the Hamiltonian times t. That's our dimensionless time. And that's given by pi on 2, pi n on 2. N on 2 times pi is the simulation time that we have. And if we want to beat that error, so if we want to beat the error, then we have to perform n on 4 is t on 2 pi queries. So the key point here, I know I'm rushing through it, but the key point is that the number of queries required can be related to the time of evolution, right? The time of evolution is proportional to the norm of the Hamiltonian, so it tells us that the time required, that the number of queries required puts a lower bound on how long it will take to simulate this Hamiltonian. So the result is that this Hamiltonian evolution requires a time scaling proportionally with t to simulate it. Remember the idea of the counterexample. So the counterexample is saying if we can find any Hamiltonian that cannot be simulated in time less than t, that's sufficient to claim that there cannot exist a general algorithm that will do a sublinear in t result. And then the idea is simply augmenting a spin system by an ancillary qubit to see whether we can, and not to violate the lower bound proof. And then here's this again, so you understand what's going on. We see that this evolution is crossing between spheres depending on whether the string of bits changes value or not. There's the clock running up to time pi, so we evolve up to time pi and get a result over here, and it landed on the blue sphere. That tells us the result for the parity of the string of bits, and in some time, and the time scales with n, which is the norm of the Hamiltonian, and therefore, in the end, we have a result that can't be sublinear. Okay, so to recapitulate, we've dealt with time. We're going to go to another issue in a moment. But with respect to time, we now know that we have an algorithm that brings the time cost of simulation, like the number of pulses, down as close as you like to t, but it can't go less than t. So you can't do better. So we've now hit the point where we say we have a good quantum simulation algorithm that's as good as it gets. We can stop working on that. It's not entirely true. There are different variations, and I'll mention them. But roughly speaking, the Aronoff and Tashma established the efficiency of simulatability. This establishes the best you can do. Now, I want to get to another part, which is how do we get these one-sparse Hamiltonians? So if you're given a general Hamiltonian H, and you want to then figure out what is your sequence, like a pulse sequence. Ray mentioned GRAPE, the gradient ascent pulse engineering approach, etc. There are various things that people do to try to build these things up. At this level, we're going to abstract it all and say, we simply say that we have a given Hamiltonian evolution, and we want a general algorithm that will always tell us the best way to get the sequence. So I'll explain this here. This is borrowed. So these slides were actually done by Richard Cleve, who does very nice slides. So I'm just going to use his slides and I don't even bother to redraw them. But he was a collaborator of mine on this work, so I don't feel badly about using his slides here. So the idea is the following. Given a Hamiltonian, we need to break it up into a sum of one-sparse Hamiltonians. You get it? So a Hamiltonian is a matrix, got lots of different elements in it. All we're promised is it's sparse, which means that no more than a polynomial function of n elements are non-zero, and the size of the matrix is exponential in n. How can we write the Hamiltonian matrix as a graph? And here's the way that we do it. Consider, so if I take a Hamiltonian matrix, we want to talk about the xth row. Let's say x is 20. So let x equal 20 be the 20th row of the Hamiltonian matrix. And then let y1 be some column. So for example, let's say this is the 20th row, the 4th column, and the 14th column. Then we're turning it into a graph. We're saying that the 20th row, 4th column, has a value of the matrix given by alpha 1. In graph theory language, this is the weight of the edge. These are vertices, that's the edge, and that's the weight. The 20th row, 14th column has that value. And it's sparse, so then it means that the number of edges sticking out of any vertex is only a polynomial function of the number n, which is logarithm of the dimension of the matrix. Okay, so we have a way of doing that. There's a subtlety here. If the Hamiltonian is Hermitian, and if the Hamiltonian is Hermitian, then if we say this was the 20th row, 4th column, but what if this was the 4th row and the 20th column? Then we have to join those where that's the complex conjugate of alpha 1. Turns out we can just consider real Hamiltonians for the time being. And so this is the way we're going to turn a Hamiltonian into a graph. So in that sense, here's a graph, and every Hamiltonian matrix we can turn into some graph. And as I said, the number of edges is going to be limited. In this case, no vertex has more than 3 edges. So this would be a 3-sparse Hamiltonian. Okay, now what we want to do is to take this graph and turn it into a union of disjoint graphs that have no more than 1 edge per vertex. And then we can plug it in to that child's type of circuit. Okay? So that's the goal, is we want to turn it into that, and then each one of the degree 1 graphs will generate a particular kind of pulse. So here's what we would do, is we're back to that diagram here. What we do, first of all, is we have a way of labeling. So like if this was the 20th row, 4th column, one of the tricks we have to do in doing this with the Hamiltonian is you can't just look at the whole Hamiltonian. If you write down a Hamiltonian that's exponentially big, even the fact of looking at every matrix element is an exponential overhead, which is unacceptable. Remember, we have to bound our resources. So you can't even look at a matrix that's exponentially big without incurring an exponential cost. But if you know it's only polynomial number of edges, then you ask the following question. You say, in this case, you say, I know that the 20th row has at most 3 non-zero column elements. What is the first one? Here's the value. What is the second one? What is the third one? End of story. So in order to break up the Hamiltonian in an efficient way, what you want to do is to have your Hamiltonian structured in a way that you query it by not asking everything. You say, what is the first column? But when you ask that, it's not ordered. So if this is column 14 and this is column 4, that might be okay. It might be the way it's structured, because we have to take into account hermeticity. So there's no guarantee that when you ask those questions, there's no order on which columns it's going to give. So when you ask it, what's the first, there's a consistent way that the queries will deliver answers, but not an ordered set. You don't know whether the first column returned is bigger or smaller than the second column. So now suppose that you're given a Hamiltonian and you get really lucky. The 20th row has a first column non-zero entry of 14, and the 14th row, its first entry is column 20, see, with the hermeticity. If you get lucky like that, which you almost never do, then the idea is that you can easily break this up into D Hamiltonians. So here's one. That's the red. Notice it's degree 1. No vertex has more than one edge. Here's the other one, blue, and the third one, green. So if it's a symmetrically labeled Hamiltonian, just for didactic reasons, then we have a trivial way of breaking it up into D Hamiltonians. So we can say that to simulate that Hamiltonian, and it's degree 3, we only need 3 kinds of pulses. But we never get that lucky. So putting it all back together, so you can see here, like 1 always goes with 1, 2 with 2, 3 with 3, etc. But we don't have that. So we need to consider the non-symmetric case. And what we do is we label each edge, so it's not guaranteed these are the same. So instead of D elements, they're D squared. 1 can match to 2, 1 can match to 1, 1 can match to 3, and vice versa. So they're now D squared colors instead of D colors. And so what you see here is if we say that the first non-zero column for that row is, the 8th non-zero column for that row is A, and the bth non-zero column for that row is X, then we need D squared labels to be able to color. So it just tells us how many colors we need. You get the, I don't know if people know the 4-color map problem. It was a famous problem that was eventually solved. So these kinds of coloring problems are very big in graph theory, and there was the famous problem for many years that was eventually solved. How many colors do you require to color a map? It was conjectured to be 4 and eventually proven. So it's kind of in that category. But in this case, D squared is not enough. We can get a thing where we have 1, 3, 1, 3, 1, 3. And so you see, if this has the color 1, 3, and this has the color 1, 3, and we give it the same color, then it's got 2 edges. But our algorithm in our quantum simulator can only deal with 1 sparse Hamiltonians. So if we have to have 2 edges, it's not a good enough coloring algorithm. Our algorithm will not function. This is why Aharonov and Tashma had the end of the 9. This is why Childs had n squared. And they're big costs. And this is how we brought it down to log star n. So, log star n, as we discussed last time, can't be bigger than 4 if you just consider all the number of particles in the universe. The iterated logarithm is no bigger than 4. And so I'll show you how we do it. So we're able to bring that cost down enormously, and that enormous breakdown of costs is what brings the time cost down. So the way that we have to worry about it is the following, that our algorithm has to take into account the unlikely but possible case of what we call long monochromatic paths. So you can see here the labeling is set up such that almost every vertex has only one edge of one color, but occasionally you could get a long path. See, it goes all the way around here. So the question in the algorithm is, how do you then color a long path with as few colors as possible? Because every color is another type of pulse sequence. And so here's the problem we have to deal with, which is the long colored path. And so one obvious way would be, suppose instead of making it red, we consider maroon and turquoise. So we just did a maroon, turquoise, etc. The problem is we sneak in a very high overhead. So if we start, it's exponential. So if we start, if we do red, if we do that, it's fine. We could make every one a different color. So we could say, let's color each of these differently. Then we wind up with an exponential overhead. We can't make them alternating. It turns out it doesn't work. And so here's the way that it can be done. And so this makes use of a computer science protocol that has an oxymoronic name known as deterministic coin tossing. And I'm going to show you how it works. And this is where the log star n comes in. So here's our long monochromatic path. This is vertex x, y, z, w, etc. So we have this long monochromatic path. And remember, they're all labeled by AB. AB is the color. So in that picture, they were red. So the value of AB is red. Then we want to be able to color that in as efficient a way as possible. And the answer is the following. This is very clever, how the clever stuff was done by Cole and Vishkin. And the way that we do it is, let's consider the following. Let's first give this a color where this is the color ABY. So it's the AB, the red color. And then we make shades of red, a different shade of red for every vertex. So we have this exponential overhead. Then this is ABZ. And so we have two different shades of red labeled in some way that puts an exponential overhead. But we're not done. What we do is we bring it over to here, and what we ask, and I'll explain this better in a moment, but what we ask is we want to find a way to label this that will cut the cost exponentially. So let me show you exactly how that works. Suppose, so they got the same AB, it's just different shades of red. So the shade of red for vertex Y is written as a bit string. The shade of red for following vertex Z is a different string. All we want to do is to find a way to know they're different shades. We're going to take all the shades of red and reduce it to as few colors as possible. I'm going to show you we can reduce it to 6. So it turns out that if you have a long monochromatic path, all you need are 6 colors. In fact, if you look at the implicit result in the Harman Fantasma, it's much, much bigger. So it scales up with we get a constant. So then we have this, and then all we care about is whether they have the same shade or not. So we just say, in the bit string, what is the first significant bit that's different? And then we store which bit is different and the value of the bit for the first of the two vertices. See? So it's the 0th bit, and that value is 1, and we put it there. So what we've done is by asking not what that long string is, but what is the different first significant bit, we've cut the cost exponentially. So we started with an exponential number of shades of red, and now we've cut it down. But we don't need to stop here. We can do it again. So that took us from 2 to the n colors for n bits. Now we only need to store in log n plus 1 bit. So we just saved exponential. But let's do it again. So we do it for all those. And then we do it again. So we say, okay, now we have the different shades. Let's take it to the next step and shade it again. And we then say, now we're on log n bits, but now we say all we need is the first different significant bit here. So we do the same thing. This brought us from n bits of storage to log n bits. We do it again, we get the log of n, roughly. You see? So if we keep doing that, we keep taking the log of the log of n, etc. And so the number of queries is the iterated logarithm. That was the log star n. Okay? So if you had 10 to the power of 10 to the power of 37 bits in your computer, you only need 5 steps. And that's inconceivable. Imagine a quantum computer that has more particles than a billion universes all put together. You know, much bigger. And all you need is 5 queries to get there. So it's an extremely efficient algorithm to get there. And not only that, but you only ever need a maximum of 6 shades. So if there's a long red monochromatic path, you say, well, that's a problem. I can't use my red button. This tells you that your red button is simply replaced by 6 reddish buttons with different shades. So it brings the cost of breaking up the pulse sequence into a very low number. So the number of iterations is order log star n, and the number of steps it requires to get to 5 elements is at worst 5 iterations if your quantum computer had 10 to the power of 10 to the power of 37 bits, qubits. Yeah? I don't know. No, not related. I know what it's called. Yeah, it's not related. Okay, yeah, it's not connected as far as I know. Okay, and then why 6, but I'll skip it. I kind of explained. Roughly, it turns out that all we need is the bit required for the last position. Where is the last significant bit located, and what's its value? So we only need to store 0, 1, and 2, and then we just wind up with 6 elements. And that leads us to the result. This NBB is really the number of pulses we need to affect. Once we do all that, we find that the number of pulses goes almost linear. We're able, and the multiplying factor here is the log star n. And so we've brought down the quantum simulation algorithm down from just an in-principle efficiency argument to something that looks sort of viable. I mean, if we get into the details later of how many gates you need, I'm going to have to give you some bad news. But the good news is it's the best you're going to do. So at least we have an idea of how many gates it requires to do things. But once you get into the real numbers, it's scary. Okay. And it turns out that the number, because we need at most 6 shades, it turns out that the most types of pulses you need for a given d-sparse Hamiltonian is 6 times d squared. So if you ask the question, you say, I have this Hamiltonian. It's d-sparse. How many different types of pulses do you need? I can tell you that the upper bound is 6 times the square of your sparseness. So we have a nice upper bound on that, and it's actually a cute graph-theoretic result that's of interest now in graph theory. It's one of those cases where you solve a problem in quantum computing and you discover something that actually is interesting in mathematics. Okay, so that gives you an idea of what we did back in 2007. Me, Richard Cleve, Graham Mahokas, Dominic Berry. And then there was further work done, and I'm just going to give you a sketch of this. And so the idea is there are various clever things to do. One is by Andrew Childs again and his student Kotari, 2010. They used the same deterministic coin tossing I was just explaining to you, but instead of coloring edges, they color vertices. And so we heard the question about the small networks. So one of the things in networks is you consider topologies. We didn't make a topology argument of the Hamiltonian. So the Hamiltonian graph, we didn't put a topology on it. But if you take your topology such that you decompose the Hamiltonian into a sum of galaxies, so you form these different galaxies like nodes in the network, then they're able to bring the time cost down here, the D part. They use our Suzuki Trotter-Suzuki approach. Their space cost goes up a bit. So if you start doing some topology on the graphs related to your Hamiltonian, you can do some clever stuff. Dominic Berry, who was on our work, and he and Childs worked on another approach which makes use of the Kitaev phase estimation type algorithm, and they were able to bring costs down a lot, but their epsilon error goes up. So the time cost is very sensitive to the error tolerance, but it takes the time. The time is actually linear here, and there's a scaling with the maximum norm. Okay, so that kind of gives you an idea. There's more work going on. It's really fun if you have a mathematical heart, because then it's got the physics in it, but it's kind of elegant because you map your Hamiltonians to graphs, and you can start using graph theory to design better quantum simulation algorithms. So it's very beautiful. Okay, now I want to go back to, now I'm going to leave aside this abstract mathematics and go on to what's happening now in quantum simulation in the experimental world, to give you a feeling for that. And remember what I told you a couple of days ago. I said the point of quantum simulation is to simulate the Schrödinger equation. And the Schrödinger equation simulating the Schrödinger equation is not particularly well defined. You could look for the spectrum of a Hamiltonian. You could look for the eigenstates. You could look for the state evolution. And the stuff that we're doing is very close to Feynman's own concept that the idea of a quantum simulator is to deliver expectation values of observables as they change over time. So now we're going back to the roots of what I talked about a couple days ago. And we have our Schrödinger evolution. And now let's see what interesting questions can be answered. So far I've been talking about how we actually design our algorithms to simulate. Now let's go back to the issue of, let's say we have our quantum computer, we have our algorithms, what are we going to do with it? And this takes us back to the Abrams and Lloyd work, which I believe I mentioned briefly on a couple of days ago. And so the Abrams and Lloyd work suggested simulating quantum field theories. And this area is going very nicely. Yeah, we have, like, I saw Levenstein's talking next week on simulating lattice gauge theories, for example, at the conference next week, etc. So there's a number of, this area is really taken off. Anyway, this is the Hubbard Hamiltonian. And the Hubbard Hamiltonian is written in terms of fermionic operators. And so in this paper by Abrams and Lloyd, they recognized that Feynman's work already showed how to simulate bosonic quantum field theories. So the trick here was to show how to take a fermionic theory and map it over. And there's also the Bose-Hubbard model discussed there. And we have, and there was a later paper that showed how to simulate anionic quantum computation. And so we know now, given these algorithms, we know how to take a field theory, map it over to a way of representing it as qubit operations on a quantum computer, and then we can use these simulation algorithms to simulate what's going on. These Hamiltonians are interesting. In case you don't know, the Hubbard model is famous for explaining how a material goes from being a conductor to an insulator, and it's also famously intractable in higher dimension. So if you want to ask questions about the Hubbard model, conductor to insulator in 3 or more dimensions, you probably need a quantum computer to answer these questions. The Bose-Hubbard model explains the Mott insulator, Bose glasses, and superfluidity. And the point that Abrams and Lloyd say in their paper, they make the following point. They say, well, thousands of qubits and billions of quantum logic operations are needed to solve classically different factoring problems. And in fact, they're underestimating it. I won't tell you now, but the number of qubits you really need is worse than what they're saying. They do point out it would be possible to use a quantum computer with only a few tens of qubits and a few thousand operations to perform simulations that would be classically intractable. So the idea is not to try to reach scalable quantum computing, but rather, can we build a quantum computer with or without quantum error correction that will be able to deliver an answer to a question related to one of these Hamiltonians? We can't verify it because it's not tractable, but we trust it. We say, yes, we believe this quantum computer is working. We trust the answer. And so this is why the quantum simulation area is so hot right now, is we know when we take a moment and think seriously, we think, yeah, this factorization is way too hard to conceive of in our lifetime. What can we do with a quantum computer in our lifetime? And I don't care how young you are, it's the same lifetime. That whether any of us are going to see factorization, I doubt it, even if you're 1 year old. But the idea of seeing a quantum simulation is tantalizingly close. It is possible. So then if we can do it, we can start simulating properties of quantum materials, etc. And the way that it works is that we want to be able to take these spin systems. So I just put up examples. I'm just trying to give you a flavor for how these things work. So when we take a quantum field theory of some sort, then what we do is we map it over into a set of operations on qubits. So this could represent some array of qubits, and then we can consider like an Ising Hamiltonian. We can consider XY, Heisenberg, Hubbard, Bose-Hubbard, etc. And each of these essentially maps over to a set of Pauli operations, X, Y, Z, acting on an array of qubits. So that's the way that we do it. Once we get to that point, then we have a Hamiltonian, right? So here, each of these is represented then by a sparse Hamiltonian, and then the methods I talked about become relevant. You take a sparse Hamiltonian, and then you can decompose it into a set of operations in the Suzuki formula, and if it's not clear how to write it as a sum, like in this case it's trivial, it's already a sum of sparse Hamiltonians. If it's not clear, then you can use a coloring algorithm. And here's an example. This is what the Heisenberg model looks like as a matrix, just so you're clear on this. This is the Heisenberg, the Hamiltonian for the Heisenberg model in one dimension, and The sigma I is just the vector of the 3 Pauli operators dotted with the 3 Pauli operators on the next spin half particle in the chain. And if you write it down, if you take just 2 qubits in the Heisenberg Hamiltonian for a one-dimensional spin chain, you can see it's too sparse, right? No more than 2 non-zero elements in any row or column. If you take the Heisenberg Hamiltonian for the spin chain of 3 spin half particles, the sparseness is 3. See? So I'm just writing that Hamiltonian as a matrix. So you can see here, if you take 4, look how big it is, 16 by 16. The matrix is growing exponentially, but the sparseness is only linear. So these physical Hamiltonians are all naturally sparse. And you can do it with any of the other ones. It's actually a good exercise just to go through. You know, you take these Hamiltonians we deal with, say, in condensed matter physics, and it's nice just to write them down as a matrix representation, get a feeling for it, and you see my point then. I can write each of these as a graph, and then I can start coloring the graph to know how to do the simulation of the evolution of the system. And as I mentioned 2 days ago, one of the arts of theoretical physics is to find the problems that are easy to solve and use that to get insight. The point here is the opposite. We don't want to find the easy problems to solve. We want an algorithm that will solve the general case. We want to solve the hard problems. So that's why I'm giving you all these techniques. If we have a quantum computer, we don't have to look for the easy problems to solve. We could just run it on our quantum computer and get the answers. Here's just another picture. And this picture is Kitaev's honeycomb lattice. This is of interest if you get into anyons, creating anyons. And this one, again, has a very, the lattice structure is not rectangular. It's got a different structure. There's a Hamiltonian for it. And so the Kitaev honeycomb lattice can be mapped over and simulated on a quantum computer. By the way, which I mentioned before, but just to emphasize, we could turn it around and do like topological quantum computing based on anyonic realizations and simulate back. So I always assume a quantum Turing machine in everything I do to simulate, but a lot of the stuff that we simulate efficiently can itself be a different model of quantum computing and used the other way to simulate the quantum Turing machine. Remember, the quantum Turing machine I talk about is Deutsch's version of a quantum computer. Okay, so that gives you an idea of problems, near-term problems that we want to simulate, but in fact, people are already starting to do the experiments. And for this, I want to introduce you to some language that appears a lot in the literature. And you'll see the terms analog and digital quantum simulator. You'll notice that when I talked about it at the beginning, I talk about a universal quantum simulator. So I stick ideologically to the Feynman notion. But the quantum simulator concept has broadened out a lot to the point where it's not particularly well defined. And in fact, you'll even hear the term quantum emulator come in. And the quantum emulator is even more weakly defined. But I'll give you an idea of what these terms mean. And there's a very nice paper published in Science in 2009 by Baluta and Nori that lays down a conceptual framework for discriminating the two. So when people talk about an analog quantum simulator, what they're really saying, it's like if you know about analog gravity. Let's say you want to study black holes. And you can't study the black hole, so you get some sort of a fluid, and then you say the speed of sound represents the speed of light, and then you kind of study black holes by saying, I believe that this fluid has equations governed by similar equations to a black hole. I believe that the speed of light is represented here by the speed of sound, and then everything I learned by playing with this fluid teaches me something about black holes. That's the kind of reasoning. That's what the analog quantum simulator is. It says, I construct a system that I believe behaves in a mathematical sense like the system I want to understand. And so that's the idea, that they want to just make a system that behaves like what they want to study. That's the most common kind in experiments. For example, the atomic type experiments. I looked at the schedule next week briefly, but when Levenstein talks next week at the conference, probably he'll be talking about the analog quantum simulator approach. These things, and if you know work by Emmanuel Bloch, mentioned him at lunch, and various others, that's what they do, is they construct these analog quantum simulators, and the idea is to try to test models of quantum magnetism and superfluidity and so on. And there are all kinds of big questions. Does the mathematics that we use to understand quantum magnetism really apply? They're not tractable. Let's build a system whose dynamics we believe are following the same equations, and let's see if our collection of cold atoms will exhibit similar phenomena to quantum magnetism. The digital quantum simulator is much closer to what I'm talking about. I'm talking about a programmable universal quantum computer. What I'm saying to you is, here is the way to take a quantum computer, and given a Hamiltonian, here's the sequence of steps to do it. So the digital quantum simulator is what people now call the universal quantum simulator, and that's the idea that you make a quantum simulator that can simulate any reasonable system. And now you know what reasonable is. It's a sparse Hamiltonian. So if it satisfies the sparse Hamiltonian lemma, it's reasonable. So it's a universal one. Or we could build it in a more restricted sense. There's a big fuss, for good reason. For example, the boson sampling, there were about 2 weeks ago, there were 4 papers, 2 in Science, 2 in Nature, on the boson sampling, and that's a quantum computer that is not universal, but it's meant to answer a specific problem, and it's still digital, simulating the photon coincidences from an interferometer. Okay, and the idea is that in the digital quantum simulator, you have a sequence of gates, and each gate is generated by a Hamiltonian, and that's the point of these lectures I've given you, is we now see how to turn a unitary evolution into a sequence of gates in the computational sense. And there are ways to do it. There's some work I did, if you look it up on New Journal of Physics 2 years ago, Nathan Weeb and Sadek Raisi and I. We did stuff. I don't think I'm going to go into it because I'm getting tired and I'm sure your brains are full too. So, but the idea is simply a way of taking generic Hamiltonians that are tensor products of Pauli operators and being able to write it as some efficient input to the system. So I think I'm going to skip that. These are just, I just gave examples on how to take these kinds of Hamiltonians and actually write them as inputs with an algorithm that will design the circuit. So just to be clear, the idea is that once you're given the Hamiltonian, you have to turn the Hamiltonian into a circuit. So what we've been doing is writing efficient classical algorithms that will generate quantum circuits that will efficiently simulate, you see? So when you program your computer, you need an algorithm that will efficiently write the program, and then the program will generate a quantum circuit, basically your pulse sequence, and be able to do it efficiently. And so it just does stuff where if we take the Hamiltonian, for example, x cross y cross identity cross z, it generates the circuit. So a circuit that affects that gate is simply written in this fashion. You have 4 qubits there, so there are 4 qubits. And then you have, depending on whether it's an x or y, so the x one has a Hadamard controlled not, the phi transformation controlled not, and back to Hadamard. If you have, the S here is what I call R in my lecture 2 days ago. If you have a Y, then you sandwich it like that. If you just have an identity, it doesn't interact. And then the Z operation is the one that controls acton. So it turns out that we have a way, once we decompose and write our sequence of Hamiltonians, we then have an algorithm that maps it out and creates the circuit. Okay, so everything's there. It just says, once we have all this, you just write one big program. You say, here's the Hamiltonian I want to simulate. We just put the circuit, and then an experimentalist would look at this and say, okay, I have 4 qubits. I need that operation, that operation, that one. Next, I need that. Next, I need these controlled operations. And they can completely make this happen, of course, with errors. But that circuit is then meaningful in a laboratory. Here, by the way, is what Baluta and Nori suggest as the promising technologies for quantum simulation. That was 4 years ago. Time has moved on. But just to show you what they had in mind is the optical lattice, cavity QED, and QED, quantum electrodynamics, using photonic crystals. They were also considering trapped ions, linear trap in a square, or some other complicated arrangement of ions in some Wigner crystal of some sort. And then there's the electronic versions, and this is electrons, exotic electrons floating on superfluid helium. And you have Josephson junctions and electronic circuits. So the idea is to make use of electron spins of various sorts. So that's what they suggested. I want to mention, this one I want to tell you about. This got a lot of fuss a couple of years, 3 years ago now. And so this one was very exciting. And in fact, I don't know if people heard the news 2 days ago that Sirac and Solar won the Wolf Prize. So the Wolf Prize, in most people's view, is the one below the Nobel Prize. So whenever you see a Wolf Prize going out, you can bet 50-50 they're in line for a Nobel. So Solar is here, and Ignacio Serac, those two are the guys that wrote the paper suggesting the Eintrap quantum computer, and Solar and collaborators suggested a Rydberg quantum simulator, and the idea is trying to make a gas of Rydberg atoms, and Rydberg atoms are simply atoms where the electron is highly excited. So you think of an atom as very small. These things have atoms with electrons excited to principal quantum number 50 or 60. The atom is the size of a bacterium. So they're big atoms, very fragile, and they have a proposal for trying to do, here's the Rydberg atom simulator. I won't go into it. It's got two different kinds of atoms, and it makes use of what's known as a Rydberg atom blockade. It's a blockade mechanism. I think, who's talking about? Did you, Steve? You talked about the blockade. Yeah. So, yeah, a little bit. So Steve talked about in his lecture about the blockade, and so it's another kind of blockade mechanism. And the idea is to get the Rydberg atoms into some sort of cells. These kinds of cells are very exciting now, of course, for topological quantum computing. And so the idea is to try to get these cells, have a control atom that turns things on and off, and then being able to use these topological qubits. And so there's a lot of work going on there. Another area that's big in the quantum simulator, and this is the only set of experiments I know that work in the digital quantum simulation regime. You can say H is equal to H1 plus H2 plus H3. H1, H2, and H3 all commute. In that sense, the decomposition gets to be fairly trivial, and it keeps the gate sequence low. But if they get to the universality with more complicated Hamiltonians, then the sequences get longer. And here you can see that they're doing 100 gates and 6 qubits, and they're getting decent fidelities, not scalable by any means, but they're doing that universal digital simulation. This was out in Science back in October 2011. So, and there's a lot of work planned right now to start doing these experiments in quantum simulation. Okay, I'm gonna start coming to a close. So I'm gonna skip. I'll just go through slides, but I'm not going to discuss them. If I had enough time and energy, I was going to talk about the time-dependent Hamiltonian evolution and how to deal with that. Actually, I'll just mention some words here. Everything I've talked about right now deals with time-independent Hamiltonians. And I mentioned at one point, and we heard this morning about adiabatic quantum computing. And of all the models of quantum computing, adiabatic is the most troubling because we don't have a good model of quantum error correction. Ray mentioned that this morning in his talk. Remember that the adiabatic, he's got it up here, right? Here it is. Talked about it this morning, and the difficulty of trying to establish a good quantum error correction mechanism. One of the values of the quantum simulator is that we could actually simulate adiabatic quantum computing on a quantum computer and then test whether it's correctable or not. But everything I talked about so far is useless because the Hamiltonian is a matrix of constants. Even the decomposition of a matrix of constants. In the time-dependent case, we have a matrix of functions. And so the idea here is your Hamiltonian is no longer a set of constants, but a set of p-differentiable functions that you have to worry about. There's a lot of mathematical physics there, including operator algebra, so it takes some big thinking about it. There's a theorem on it, etc. I'm going to skip it. We even developed a Suzuki iteration. We even found that Suzuki made a mistake in a paper. Incredible. He didn't. His mistake was only. It's kind of a low-level mistake. He had a theorem, and we found a counterexample to the theorem only by finding some ridiculous Hamiltonian that had a crazy singularity over time. But a theorem's a theorem. If you find a counterexample to a theorem, it doesn't matter if your counterexample is crazy. Anybody who does analysis in mathematics knows that you can use Cantor sets to disprove things, and Cantor sets are crazy, and yet they're perfectly good ways of disproving things, disproving conjectures. And so we fixed all that with the time derivative superoperator. What Suzuki did is he kind of dealt with the time derivative as a superoperator, but it turns out it has a very bad norm. So we repaired his theorem by finding appropriate norm for a time derivative, fixed it up, and now we have a very good theory for quantum simulation of time-dependent Hamiltonians. Everything's in place to do a simulator for adiabatic quantum computing now. We've optimized our choice of Suzuki expansion. So once we fix it, his theories on lambda dependent, so time dependent or decay-dependent operator exponentials. Everything carries forward once you fix that time derivative. Skipping it, skipping it, skipping it, skip, skip, and skip. You got the flavor. Okay, so now I'm about ready to close. So I've skipped all that, but it's terribly important, and everybody should spend tomorrow not relaxing, but reading all that stuff. And then the point I want to get to now, so the idea is that, here's the message I want to give you, that so far I've talked about the quantum simulator, and I've focused on Schrödinger's equation. We all talk about this quantum simulator as a tool for simulating Schrödinger's equation, or the Dirac equation in relativistic quantum mechanics, or the Klein-Gordon equation, or quantum field theories, or whatever. But the point that you need to remember is we're simulating a wave equation. Why do we need to only focus on that? You see, just because Schrödinger's equation is our motivation doesn't mean it's our end goal. And in this beautiful paper, Seth Lloyd pops up again. He's kind of the guru, the guy with all the insight in the simulation area. And so he worked with R.M. Harrow, who's just moved back to his roots. He's back in physics at MIT now, and Avi Natan Hasidim. And so the three of them had a nice paper out in PhysRev Letters back in 2009. And it's got that funny symbol on it, which means it's an important PhysRev letter, not just your average PhysRev letter. And so then the idea is, they said, and I know you can't read this, but I put this here to give you the idea. They said, let's consider a system of linear equations. So consider the following problem, and you get this when you're, when you're a child and you're in school and you learn about, some algebra problem, ax plus b equals c, that kind of thing. That's what we're talking about. We take a matrix A, multiply by a column vector x, and let it equal b. It's inefficient. The idea of solving a linear system of equations is inefficient in the sense that the resources required to find the answer to that algebraic problem grow exponentially with the logarithm of the size of the matrix. Okay? So it's polynomial in the size of the matrix, but our problem size is logarithmic. It's the number of bits required to represent it. So if a matrix has a certain size, you say, how many bits does it take to write the matrix? It's logarithmic. It's inefficient. What they show in this paper is a quantum simulator can make that efficient for some questions. So the idea is we have the matrix times the vector is a vector, and they simply take the solution they don't know, and the vector b, and write it in a string of qubits. And once you do that, you can see, once you make this a ket and this a ket, you got Schrödinger's equation. You have an operator times a vector is a vector. So then what they do is they write it down in some basis. They use the quantum simulator in the Kitaev phase estimation approach. I mentioned before there was the Childs and Kotari approach to quantum simulators. Uses Kitaev's phase estimation, which is the heart of the Shor factorization. And then they do a simulator on it. Look at that. So you can, we made a quantum simulator, we don't just have to have fun solving physics problems. We can start solving linear equations. But there's no free lunch. So the problem is, of course, that's exponentially large in the term of the number of bits to write it. So you can't look at the answer. If it solved the problem and you look at it, looking at it is exponential. So you can't look at your answer. Problem always in quantum computing. So what they point out here in a way you probably can't see, but I have it on the next slide. Let me just read it, though. Well, no, go to the next slide. Oh, no, here it is. It says there's an x dagger mx. So I'll just explain, then I'll go to the next slide. So the point is they're saying you don't solve the linear equation to get the entire value of x. What you do is you think of some matrix M, and for some matrices M, you'll get the scalar answer x dagger mx. Okay? That's exactly what Feynman was talking about when he invented the field of quantum computing. And I went through this in my first lecture. What did Feynman mean by an efficient, well, he didn't use the word efficient, but simulatable. It was the observables. What is an observable if we turn it into a set of linear equations? The answer is, if we take x as like a ket vector in quantum mechanics, bra x observable ket x is the expectation value of an observable. So for the right observables, then we get the answer. So let me give you a fanciful way of thinking about it. Suppose that we take a model of the weather on the planet Earth. Now, of course, it's all nonlinear. We know that from 1963 and Lorenz's work. But if we take it and we say, we happen today to be in a regime where we can linearize the equations describing the weather in a reliable fashion, then we can have a set of linear equations telling us the weather on the whole planet. Then we use our quantum simulator. It won't answer every question, but you can say the question might be the observable of whether it will rain tomorrow in Bangalore. That might be a matrix M where we do get an efficient solution. You see? We don't actually know which ones can be efficiently solved and which ones can't, but it's very tantalizing that we can go with the quantum simulator beyond simulating physics or chemistry to an abstraction of simulating linear equations. And Dominic Berry went on to also show that you can use it as a differential equation solver. So it might be that if we make a quantum simulator, we can solve questions in better realms. For example, the stock market. Let's say we get lucky. We're checking the stock market. We suddenly get to a regime where the stock market has 10 minutes of linear behavior, plug it in our quantum simulator, find the right stock, and buy it. Of course, it fails when everybody figures it out. But if you're the first one that figures out that you can use your quantum simulator for that kind of thing, then you're in luck. And actually, I mean, at lunch we were talking a bit about Chern-Simons theory. So when Simon did his Chern-Simons theory, he went off and founded a company, Renaissance, and instead of continuing to do physics, he became one of the richest guys in the world. And he has this company in New York, and he hires theoretical physicists to work there. And so it's exactly this idea. In fact, he hired a lot of quantum information people recently. And so I don't know if a quantum simulator is coming along, but these ideas are interesting well beyond physics and chemistry. And we scientists need to think about that. And then the strategy they have, which I roughly described, I've just put down here that in the Harrow, Hasidim, and Lloyd work, they make use of Kidder's eigenvalue estimation, which is the heart of the Shor algorithm. You have an input vector B. You approximate it using that phase estimation algorithm. That takes order n log n steps. And then using the Kidder's quantum algorithm, the same as the Shor stuff, it gives an output, and then the outputs are used to somehow rotate and find the solution. And I don't have time or energy to go through all that. And so, so that kind of gives you the idea of how it might be valuable for that purpose. Okay, so the idea. So I just want to give you the idea that we in quantum information have to not just focus on the Shor algorithm, etc. In fact, you can see the Shor algorithm heart is living here, but it is possible to find new algorithms. It is possible to make use of the quantum simulator, and it is possible to make use of it to solve interesting problems without worrying about the big problem of scalability. We don't need to have 100,000 coded qubits and 1 million gates to be able to solve Shor's algorithm and do something interesting. There may be things we can do with a few dozen qubits and a few hundred gates that will actually answer interesting problems and maybe even get us all rich. Thanks.
Does Presco's paper extend these ideas to quantum field theory? Or?
Yeah, so you're asking about the Jordan Lee Preskill work? Yeah, so Jordan Lee and Preskill had a paper out in Science a few months ago, June 2012. And in that one, they're dealing with the quantum simulator in the sense I talk about the quantum simulator. In fact, they use some of our results in their paper. And the idea is, okay, so instead of Schrödinger's equation, we want an equation which is manifestly relativistically covariant, right? So then the idea, everything I talk about, space and time are somehow separated, right? And then the idea there is they consider how to get the simulator to it's a phi to the 4 theory, right? They're dealing in quantum field theory. There's phi to the 4 theory, which is a very nice scalar field theory, good normalizability properties, etc. And they take the phi to the 4 theory, and they use lattice gauge theory type ideas and the trotterization concept, but they use the Trotter-Suzuki that we did. And then, but they don't actually fully write the algorithm, but they make a convincing argument that the quantum field theory is efficiently simulatable. And it goes down, again, it comes down to the discretization of space-time and not just the discretization of time. You see, like the idea was, remember I keep emphasizing that Lloyd's key contribution in his 1996 science paper was the trotterization. Feynman hinted at it in his paper. Lloyd trotterized it. And so a key element of the Jordan Lee Preskill work in Science last year is to extend trotterization from time to space-time. But there's a lot of open questions. It's actually very interesting. A lot of people are trying to get into it. The trouble most people face, of course, is that they're experts on quantum computing and experts on quantum field theories, and the intersection of the two is very, very small. So there's a number of people I know trying to get into the various field theories, but even identifying the interesting problems can be a bit tricky. There's a very nice blog by Scott Aronson, Shuttle Optimize, and he writes about this, and he's writing as a computer scientist at MIT, trying to figure out what was the interesting part of the paper. And he's really identifying the continuum of space-time and discretizing it as the interesting part, which is what I find interesting. But it's hard, like in some sense you think, well, like I took Hubbard models and all that. Like we already know in a sense how to take it. But I think it's a discretization. What? Oh, what? Is what sparse? No, which, you mean the Jordan Lee Preskel Hamiltonian or what?
The sparse Hamiltonian.
Yeah. No, I know what a sparse Hamiltonian is. I just don't know what you're asking me.
Is asked as some graph, correct? It is represented by the some graph.
So I can answer a question if I understand it, but you've got to make the... Can you turn it to a decision problem? So I can say yes or no? No?
Have we rather that graph? That is my question.
What?
Each sparse Hamiltonian has some graph, correct? It is represented by...
So you're saying, does a sparse Hamiltonian have a graph? Is that the question?
Yes.
Okay, so I'll rephrase it slightly as saying, you're asking me, does a sparse Hamiltonian have a representation as a graph? Every matrix has a representation of a graph. A sparse Hamiltonian has a representation.
Symmetric and unsymmetric. There is 1, 2, 3. He's mentioned by some colors.
Don't understand the question.
No, you can ask him in private.
Yeah.
Other questions?
Nobody wants to know how to get rich?
Tell me how to do it for a quantum field theory in curved space-time, I'm sure.
Penrose wrote about that, didn't he, in his book, Emperor's New Mind. If you have the curved space-time, you get a loop in time, you can somehow, close time loops or something. Yeah, maybe. Yeah. Yeah, and we just have to live in a universe where it's consistent that we got rich.